Welcome to AP Podcast 8.7. This is we're going to spend a little time on the covalent bond and bond energies and calculating some bond energies. So just as a quick review of the covalent bond stuff, this is the same kind of thing that we were looking at when we were talking about ionic bonds. The tendency of atoms to achieve a lowest energy state is why we form a covalent bond. It's not by an electrostatic attraction, but it's more by a sharing of electrons. This is a little something from your book that I thought was kind of interesting because I don't really think about this too much, but bonds don't exist in nature. Oftentimes when we draw models, we'll go like this, and we'll go like this, and we'll represent this little stick right here will represent a bond. Well, there's no hard, sticky thing that keeps atoms together in nature. It's just the way that we look at things to help us understand what's going on and what are the energies involved. So speaking of energies, chemists have calculated the energy of each bond. And this is a little side, not something that's critical for us to understand as far as passing an AP test, but it's just still good information. It turns out that every time you break a bond, it's going to require some energy. And when you break a bond of one thing, for example, we get a methane going to a CH3, that's going to take a certain amount of energy. Well, now we're going to take that and try and break off another hydrogen. That's going to take a little more energy. And notice this one goes up, this one goes down, this one goes down also. I don't know of any rule that tells you exactly what's going to happen, but it's just important to know that there is a little change in energy depending on how many bonds you're breaking, which is why when we do these kind of calculations, we want to use averages, and so we're always trying to get a close approximation of what the real answer is. So speaking of averages, if you were to look on page 327 of your textbook, you would find a table that gives you the most common bonds there are and the energy it takes to break them. And just as a little review, this is stuff from the past. Single bonds are one pair of electrons, double bonds are two pair of electrons, triple bonds are three. And what happens is when you have more bonds, you get a shorter bond length. And if you look on that table, you'll see that the molecule are actually the bonds that are shorter and are multiple have a greater bond energy. Something to know, but you'll always have a table involved. So thinking about that, let's go over how we would use these bond energies to find the heat of a reaction, or the enthalpy involved in a reaction. And we've done heat of reaction with Hess's law, and we've done heat of reaction by using the table in the back of the book, but this gives us another way to do it. However, we have to be aware of a couple things. One is it takes energy to break a bond. So let's just say, for example, I've got some oxygen here, some water here, and I want to break this up into some O2 and into some H2, which is possible through a process called electrolysis. Well, if I want to do that, I've got to pump energy into this molecule in order to break that bond. So you've got to break a bond first. Now when I've got basically these H's floating around, they can come together and make a bond. And if I have some O's floating around, they can come together and make a bond to make these two molecules right here. So that's a really important concept. You've got to break bonds first, then you've got to make bonds. And so when we add up the energy of each of those processes and then subtract them, we get the change in enthalpy for the reaction. And so here's a simple little formula. The sum of the bonds broken minus the sum of the bonds formed. Now this is really important because if you remember with calculating delta S, delta H, delta G in before, we were taking the reactants, we were taking the products and subtracting from the reactants. And this is the reverse of that, right? Because the bonds broken are really what? Those are the reactants. And the bonds formed are really the products. So it's really important that you keep that in mind. When using bond energies, it's a reverse process. You've got to think of what has to happen first before we can form some products. And what has to happen first is you have to break some bonds. So let me show you a typical problem that you'll see. here's a reaction. Methane plus chlorine plus fluorine gives you these three different compounds. And then there are the bond energies that are involved in this. So what we have to do is we have to first think of all the bonds broken, add those up, all those energies, and then we have to subtract that from the bonds formed to see if we get an exothermic or endothermic reaction. So I'm going to go through this with you. And it's a little tedious, but just bear with me. So I've got a CH4. Now, a lot of times in these, it helps to draw them out in a Lewis type structure that you guys did last year. So how many CH4 bonds or CH bonds do I have? I have 4. So it's basically, and I'm just going to say these are the bonds broken. Okay? I've got 4 times 413 kilojoules. I'm going to leave off mole there. All right, so I've got that. Now I've got chlorine. So here's a chlorine-chlorine bond. But look at this. Super important, right? There's 2 chlorine molecules. So it's going to be plus 2 times 239. All right. Now I'm going to break a fluorine, but not just one fluorine. I'm going to break 2 fluorines, right? So 2 times, what's a fluorine bond right here? It's 154 kilojoules. So I add that all up and I get a value of 2,438 kilojoules. All right. So those are the bonds broken. So I've broken those bonds, and now I'm going to subtract that from the bonds made, right? Well, here's the bonds made, or bonds formed, I guess I should say. So let's do that one. Let me change colors here just so we know we're going the different thing. Now look at this beast. That might not make sense to you right away. So I'm just going to draw it out. It's going to look like this: carbon in the middle. I'll put each atom on opposite side. All right. So there's that thing. And then HF and HCl are pretty straightforward. So here we go. Let's start adding up the bonds formed. We've got 2 CCl bonds here. So let's find that. That one's right there. So we've got 2 times 339 kilojoules. Okay. Plus, I've got 2 CF bonds. Where's that? Here it is. Plus 2 times 485 kilojoules. And then I've got an HF bond, but again, we got to focus on that. There's 2 HFs. So I've got 2 times 565. Can you see how much energy is involved in making these bonds? That's a lot of energy, right? So I can already tell that this is going to be an exothermic reaction. We're having a surplus of energy. And then an HCl bond, but again, focus on that coefficient. We've got 2 HCl's. So that's plus, I'm just going to put it down here, plus 2 times 427 kilojoules. All right. And you add that all up, that equals 3,632 kilojoules. All right. So I'll put that up here, 3,632 kilojoules. We subtract them out, we get a value of 1,194 kilojoules. Okay. Oops, I'm forgetting the main thing, a negative sign, right? Okay, so that tells us that is an exothermic reaction. So there's the heat of the reaction for that reaction based on bond energies. And sometimes we'll actually look up heats of formation and work it out, or heat of reaction for each one of those compounds, and you could do it another way. So there you go. Hopefully that kind of made a little sense, and we'll talk about this in class, and see you next time.